is problem set number 6, problem 7. Consider a charge distribution that consists, roughly speaking, of two overlapping spheres of radius r. In the region where the two spheres don't overlap, the charge density is negative rho. In the region where the two spheres do overlap, the charge density is negative 2 rho. In the diagram, the dashed line connects the center of the two spheres. Note that the edge of the right-hand sphere is a distance r over 2 from the center of the left-hand sphere, and vice versa. So I'm just going to write down the givens. So I have two spheres, right? I've got the left-hand sphere right here, and I've got the right-hand sphere right here. Those two spheres overlap at a certain region, this region, right? And the charge density is different in that overlapped region, in that shared region. So in this shared region right here, that's represented by the region with the green lines, the charge density is negative 2 rho. However, in the region where the two spheres don't overlap, the charge density is negative rho for each sphere, okay? I know that the dashed lines you see on the diagram is the distance between the center of the two spheres. So this is the center of my left-hand sphere, and this is the center of my right-hand sphere, right? What else do I know? Okay, I also know that the edge of the right-hand sphere is a distance of r over 2 from the center of the left-hand sphere. Okay, so the edge of the right-hand sphere right here, that distance where point A is located, is a distance of r over 2 from the center of the left-hand sphere, and vice versa. So also here at this edge of the left-hand sphere, its distance from the right-hand sphere is also r over 2. Okay, I'll actually write that down. So this distance is also r over 2. And remember, the radius of each sphere is radius of r, right? So if this is r over 2, then that means this distance right here is also r over 2. Okay? It's not drawn to scale, I think. All right, so part A, if a point charge Q were placed at point A, what electric force would it feel? And as a hint, we're told to use superposition. All right, so for part A, I am looking for the electric force. So electric force at point A due to point charge Q. Okay? All right. In order to solve for that, I will use the formula for electric force that's found in chapter 20.4. So in chapter 20.4, we are given that the electric force is equal to the point charge times the electric field at the point where the charge is placed. Okay? So this formula we should know. That's how you go from the electric force to the electric field. And you can find that by a certain Q, the point charge. down. This is electric force. This is point charge. And then this is the electric field. At the point where point charge is placed. Okay. So I know the value of Q, right? It's given to us in the question. It's capital Q. That's a point charge value. I'm looking for the electric force. So I just need to find the electric field now. All right. So I need to find the electric field at point A. In order to find the electric field, the total electric field at point A, I'm going to use superposition to find the electric field at point A due to the left-hand sphere. And then I'm going to find the electric field at point A due to the right-hand sphere. And then I'm going to sum them up to get the total electric field. Right? So this is, let's use brown. This is point A right here. So let's use this green one. So this is point A, right? This is point A. And I have two spheres that create an electric field at point A. I've got this left-hand sphere that creates a specific electric field at point A. And I also have this right-hand sphere that creates an electric field at point A. So I'm going to use superposition to find the total electric field by adding the individual electric fields, one from the sphere on the left-hand side, and then adding it to the electric field due to the sphere on the right-hand side, right? So the concept of superposition is that every charge in space creates a certain electric field at a point, independent of the other charges that exist. So the resultant, the total electric force, is a vector sum of the electric field due to those individual charges, okay? So let's do that step by step. Okay. So step one, I'm going to calculate the electric field at point A for left-hand sphere. Okay? And I'm going to use the formula for flux to do that. So this is electric flux, okay? And that is equal to surface integral of the electric field times dA, which is equal to the charge enclosed, Q enclosed, divided by epsilon naught, or the permittivity of free space, which is a constant, right? Okay. So again, this is electric flux. Okay. This is the Gaussian surface area. And this is the charge enclosed in the Gaussian surface area. Okay. So real quick, I'm also just going to write the formula for surface area of a sphere. And everything in blue ink is something I think you guys should either know or have in your cheat sheet. So the surface area for a sphere is equal to 4 pi r squared. Okay, the volume for a sphere is equal to 4 over 3 pi r cubed. All right. Okay, back to our problem. I'm gonna make a drawing of this real quick so we understand what we're dealing with. Okay. Doesn't need to be that big, actually. Yeah, that should be fine. All right, so we've got a sphere right here. All right, and this is the center of the sphere. And it has a radius r, okay? This is the left-hand sphere, again. Only the left-hand sphere. All right, and point A is located right here. Which is a distance of r over 2 from the center of the sphere. So this distance is r over 2, all right? And then the charge density of this left-hand sphere is negative rho, right? So I'm going to put a Gaussian surface, also a sphere, around here. So that's my Gaussian surface. So my Gaussian surface has a radius of r over 2, which is the same distance that point A is from the center of the left-hand sphere. Okay? So, because the normal vector of my Gaussian surface is going to be parallel to the electric field that's caused by the left-hand sphere of charge density negative rho, then my E is a constant, right? This electric field right here, that's a constant, so I'm just going to take it out. So E, and then the surface integral of my Gaussian surface, dA, is equal to my charge enclosed, Q underscore, or subscript enclosed, over the constant epsilon naught. So the integral of the surface integral of dA is just going to be the surface area of my Gaussian surface, which in this case is a sphere, okay? And that's 4 pi r squared. So if I do that, first of all, that would be 4 pi. What is the value, what is the radius of my Gaussian surface? It's not just little r, right? It's actually r over 2. That's the radius of my Gaussian surface right here, right? So that's, well, that is what I'll input as the r. So r over 2 squared, right? Because it's r squared. That's what we see here, r squared. And that is equal to the charge enclosed over epsilon naught. Okay? Now I need to find my charge enclosed. In order to find my charge enclosed, I am going to use the formula for charge density. I'll actually write it. I guess I'll write it right here. So charge density is equal to my total charge divided by the volume, right? Or in this case, it's the total charge enclosed divided by the volume of my Gaussian surface. So Q would be equal to E, right? So let's do a little side quest to find our charge enclosed. Okay, so side quest. Number 1. So if my Q enclosed is equal to rho V, right? Again, what is enclosed? I'm asking what's enclosed in this area right here. Well, charge density doesn't change regardless of shape, right? It's like the density of a 6-foot metal bar is the same density. A stainless steel bar is the same density as a density of the 2-foot metal bar. It just depends on the material. And the same with charge density. It doesn't matter the shape. I still know that this charge density was given in our problem as negative rho. So that's what I'm going to write for my charge density. Oops. Negative rho. And then V, that's the volume of my Gaussian surface. So what is the volume of this sphere right here? The formula for volume of a sphere is here, right? We just have to replace this R with the radius of our Gaussian surface. So that's going to be 4 over 3 pi times R over 2 cubed. That's our volume, right? Again, this is the charge density of the left-hand sphere. And then this is the volume of our Gaussian surface that we chose for this specific case, meaning this case right here. Okay, so let's solve that. That becomes negative rho times 4 pi over 3 times r cubed over 8. We can cancel this out. This becomes 2. This becomes 1. So then we're left with negative rho pi r cubed over 6. That will be our charge enclosed, okay? We're gonna put a cloud over it so we know that we're gonna use it. Okay, so back to my main problem right here. Back to my main problem, right? I just had a side quest to figure out the value of the charge enclosed. So I've got E times 4 pi, and this, actually so this becomes 4 pi r squared over 4, right? Is equal to the charge enclosed, that is negative rho pi r cubed divided by 6. And then let's not forget the epsilon naught in the denominator as well, so 6 epsilon naught. Okay, so now I can find the electric field at point A for the left-hand sphere. I'm just going to move this guy to the right-hand side of the equation. So that becomes the electric field is negative rho pi r cubed divided by 6. That's r cubed. Then times, these also cancel out. This cancels out with this, so times 1 over pi r squared. Okay? So I can cancel some stuff out. Pi cancels out. R squared cancels out with this. So I'm left with negative pi r over 6. Oh, I forgot the epsilon naught right there. Yeah. Over 6 epsilon naught. Okay? So that is the electric field due to the, or for the left-hand sphere. For the left-hand sphere. And I'll put a red box around it. Okay. All right. So step 2. So that's step 1. So now step 2. Let's calculate the electric field at point A for the right-hand sphere, due to the right-hand sphere. At point A due to right-hand sphere. All right. And again, I'm going to use the same formula for the electric flux. Okay? So that becomes well, okay, before we do that, I'm gonna redraw our next thing we're dealing with. Copy. Paste. Okay, but now what are we dealing with now? So, oops. Okay, now what are we dealing with? Where's point A? Point A is right here, right at the edge. Point A is here, and that's right at the edge of the right-hand sphere, right? So let's draw that. So here I've got point A. This is the center of my sphere. And it's a distance of r, right? Because the radius of this, right, of the spheres, both spheres is r. And then I've also got a charge density of negative rho. So that's what I'm dealing with now. All right. So same as step 1, we're gonna calculate the electric field. And the Gaussian surface I'm going to use this time will be the same size as my right-hand sphere right here. So also of radius r. Okay, so I've got E, surface integral of dA, right? Everything same as step 1. I'm just dealing now with a different sphere, the right-hand sphere this time. Equal to Q enclosed, the charge enclosed, divided by the permittivity of free space, epsilon naught. Okay, so again, guys, this is my Gaussian surface area, right, that I'm looking for. So that will be E. And what is the surface integral of dA, or my Gaussian surface area? It's just the surface area of a sphere, which is 4 pi r squared. But this time, our r is this capital R, right? Because that's the radius of my Gaussian surface area. Okay, so that will be 4 pi capital R squared. And that's going to be equal to the Q enclosed. What is our Q enclosed? Let's find out. So again, the surface charge density is equal to Q over V, or the charge versus divided by volume, right? The charge density, again, surface charge density is equal to charge divided by volume, okay? So my Q is equal to rho V, okay? My charge is equal to surface charge density divided by volume. Or sorry, charge is equal to charge density times volume. All right, and in this case, my charge density is negative rho. And my volume, for my Gaussian surface, or whatever, wherever this charge is enclosed, in this case, it's just the right-hand sphere's volume. It's going to be 4 over 3 pi r cubed. Okay, so that becomes negative 4 rho pi r cubed divided by 3. That is my Q enclosed. Okay, so that's the enclosed charge for this right-hand sphere, which is also the same size as my Gaussian surface, because point A is located right at the edge of the right-hand sphere. Okay, so back to my problem. My Q enclosed is negative 4 rho pi r cubed divided by 3. And let's not forget this epsilon naught, so I'm going to add that in. Epsilon naught. Okay, so my electric field for my right-hand sphere is equal to negative 4 rho pi r cubed divided by 3 epsilon naught times 1 over 4 pi r squared. Okay, and I'm just going to cancel out this 4 pi r squared cancels out there. So I would get that my answer is negative rho r over 3 epsilon naught. And that is the electric field due to my right hand sphere. Okay. All right, so that's the answer for step 2. All right, now for step 3, let's just use superposition to find E total. Okay, via superposition. So since the electric field due to the left-hand sphere is gonna pull the, so this is the left-hand sphere, right? We have a positive charge at point A, positive Q, right? So the electric field due to the left-hand sphere is going to pull this positive charge Q to the left. Why? Because the charge on the left-hand sphere is a negative charge. So if we have a positive charge Q here at point A, it's going to pull it towards the left. Okay? And if you're wondering why it pulls it to the left, because remember a negative charge is going to be wanting to attract that positive charge. Okay? So we know that the pull, the positive point charge Q will be pulled to the left from the electric field due to the left-hand sphere. Okay? And the electric field due to the right-hand sphere, on the other hand, which is this guy, will pull this positive point charge Q. It's going to pull that to the right, because we have a negative charge on this right-hand sphere, and point A will have a positive charge Q, right? So as a result, we're going to subtract the electric field from the left-hand sphere from the right-hand sphere. So, oops. So we're just using our coordinates, x and y, right? Where anything pulling that positive point charge Q to the left will be negative, and anything pulling that positive point charge Q to the right will be positive. So E total is going to equal the magnitude of the electric field due to the right-hand sphere minus the magnitude of the electric field due to the left-hand sphere. Okay, so that's going to equal negative rho r over 3 epsilon naught minus, oh sorry, why did I say negative? I just said absolute value right here. Okay, so that's going to be rho r over 3 epsilon naught minus rho r over 6 epsilon naught, which is just the value we got here. Okay? So if we subtract these two together, we're going to get that the E total, or the total electric field, is equal to rho r over 6 epsilon naught. Okay? And once we have that, we're going to move on to step 4, where we're going to find the electric force felt by the point charge Q placed at point A. Okay? So again, we're going to use this formula from chapter 20, section 4, where the electric force is equal to a point charge times the electric field at the point where the point charge is placed. All right? So my F, or the electric force, is going to equal to the point charge times my electric field, where the point charge is placed. So what is my Q? My Q was given, right? It was a point charge of capital Q. So my point charge value is capital Q, and I'm going to multiply that by the electric field at that point, which is our E total right here. So rho r over 6 epsilon naught. And that results in the electric force is equal to Q rho r over 6 epsilon naught. All right, that's our final answer for part A. Okay? So now we can move on to part B, which is going to be pretty much the same idea as part A. So for part B, if a point charge Q were placed at point B, what electric force would it feel? Okay, so part B, just looking at that, right, for part B, if a point charge Q were placed at point B, what electric force would it feel? Let's use this color. So now we're looking here at point B, right? We're going to use superposition again for the electric fields, and using that, we're going to use this formula from chapter 20, section 4, to find the electric force that it would feel if a point charge Q were placed at point B. Looking at the diagram, right, the electric field due to the right-hand sphere, also, as well as the left-hand sphere, is going to pull positive point charge Q at point B towards the right side, since the charge on both spheres is negative, right? So what am I saying by that? I'm saying, so this is going to have, at point B, we're going to have a positive point charge Q. And because the left-hand sphere has a negative charge, it's going to push that to the right. It's going to push that to the right because hold on. No, it's gonna pull it towards the left since it's attracting that, right? Sorry, not to the right, but to the left. And the same with this charge on the right hand sphere. Because that charge is negative, it's also going to want to pull this positive point charge at point B towards the left. It's going to be attracting it, right? So because it's pulling them both towards the left, we can add them together since they're both pointing towards one direction, which is the left. Okay? All right. So, I'm going to draw that real quick. So we have this left-hand sphere. Why isn't it? Okay, so we've got the left-hand sphere with radius r, right? And then we've got over here the point charge B. Right? And actually, so here, and then we're going to have this is the center. Okay. Okay, and this is point charge B. Right, this is, so the dashed circle, that represents the right-hand sphere. Okay, I have a radius of r, and then this distance is r over 2, and this distance is also r over 2, okay? And again, this distance from here to here, that's radius r. So we have a total of 2r distance from the center of the left-hand sphere to the point B. And I'm going to make a Gaussian surface from this center with a radius of, oops. So that's a sphere, okay? That's my Gaussian surface. And it has a radius of 2r, okay? Which is the same as this distance. All right. So I'm going to use the formula for electric flux, where that's equal to the surface integral, surface area integral of electric field times dA, and that's equal to charge enclosed divided by epsilon naught. All right. So what is my total charge enclosed inside my Gaussian surface right here? Inside this sphere. It's going to be whatever is the charge enclosed in this left-hand sphere, right? So, let's take the E out since it's a sphere, and the normal vector of my Gaussian surface is going to be parallel to the electric field due to the left-hand sphere. And for this guy, that's going to be the Gaussian surface area, and for a sphere, that's 4 pi r squared. So 4 pi and times the radius squared. What is my radius for my Gaussian surface? It's 2r, right? So times 2r squared. And then make that equal to my charge enclosed. Okay, well, real quick, what's my charge enclosed? So charge enclosed, Q enclosed, is going to be equal to density, or charge density times volume, right? So in this case, my charge density, actually didn't write it down, but I should. For my left-hand sphere, that's negative rho. So this was negative rho for my charge density. And for my volume, that is going to be the volume where my charge is enclosed. So that's just the volume of this sphere, the left-hand sphere, with radius r, right? This is radius r, right? So that becomes 4 over 3 pi r cubed, and that will be my answer for negative rho 4 pi r cubed over 3. Okay, so this becomes negative 4 pi rho r cubed over 3, and let's not forget the epsilon naught, epsilon naught in the denominator. All right, and from there I can just move this surface area for my Gaussian surface to the right-hand side of the equation. So my electric field due to my left-hand sphere is going to be equal to negative 4 pi rho r cubed over 3 epsilon naught times 1 over, that becomes, so this becomes 2 squared becomes 4, and if you multiply it by this 4, that becomes 16, right? So 1 over 16 pi r squared. Okay? And this cancels out. This 4 cancels out with a 16. That becomes 4. The pi's cancel out. R squared cancels out with cubed. So I'm left with my electric field due to the left-hand sphere is equal to negative rho r over 12 epsilon naught. Okay? All right, so that's step 1. We got our electric field due to the left-hand sphere. So step 2, calculate the electric field at point B due to the right-hand sphere. Okay? So, again, we'll draw what we're dealing with. So we have a certain the right-hand sphere of radius r, right? And then within that right-hand sphere, we've got point B, which is a distance of r over 2 from the center of the right-hand sphere. So this is a negative rho charge density. And over here we've got point B, right? And that distance is r over 2. Okay? So I'm going to make a Gaussian surface. Which is going to be a sphere of radius r over 2. Okay. And I'm going to use this same formula for electric flux to find my electric field. Okay. So for the right-hand sphere, that's going to be, again, it's going to be electric field times my Gaussian surface of radius r over 2, right? That's this guy. That's the surface area for that Gaussian sphere right there of radius r over 2. That's going to be 4 pi times r over 2 squared. And that's going to equal to my charge enclosed over epsilon naught. We'll need to find our charge enclosed, which is equal to charge density times volume, right? So what is the charge density that I'm dealing with? It's negative rho, correct? Right here. However, what is the volume that I'm dealing with now in this enclosed surface of my Gaussian surface? The volume now is 4 over, that's the volume of a sphere, right? Which is 4 over 3 pi r cubed. However, for this volume for the Gaussian surface, the radius is r over 2 cubed, right? So let's solve for that. So that becomes 4 pi over 3 times r cubed over 8 this cancels out. And I am left with my Q enclosed is equal to negative rho pi r cubed over 6. Okay. So I'm just going to plug that in. So that's going to be equal to negative rho pi r cubed over 6 epsilon naught, right? Epsilon naught comes from this. And then to find, I'm going to move this Gaussian surface area to the right-hand side of the equation. So that's going to be multiplied by 1 over, sorry, not 1. Yeah, it is 1 over, I think, pi r squared. And the reason for that is 2 squared becomes 4, right? So we've got a 4 in the denominator, and we've got a 4 in the numerator, so they cancel out, okay? So then my electric field due to the right-hand sphere that will equal negative rho, oops, let's cancel stuff out first. So r squared cancels out with this cubed, the pi's cancel out. So our total, or the electric field due to the right-hand sphere is equal to negative rho r over 6 epsilon naught. Okay, so now I have the electric field due to the right-hand sphere and the electric field due to the left-hand sphere at point B. And I'm gonna sum them up to find my total E, my total electric field. And that will be part 3, right? So step 3, I'm gonna find my total electric field by summing up the left-hand sphere's electric field and the electric field due to the right-hand sphere. So both spheres have a negative charge, so the electric field from both is going to pull that positive point charge Q towards the left. So I can just add them together, right? Since they both are going towards the same direction. Okay? Okay. So the total electric field is going to equal the absolute value or the magnitude of the electric field due to the left-hand sphere plus the magnitude of the electric field due to the right-hand sphere and again, we solve for those values in step 1 and step 2, so that's just rho r over 12 epsilon naught plus rho r over 6 epsilon naught. So the total, that becomes 3 rho r over 12 epsilon naught, and we can cancel out the 3 and the 12. So then we're left with rho r over 4 epsilon naught as our total electric field at point B. Okay. And for step 4, the last step, let's find the electric force felt by the point charge positive Q placed at point B. So find electric force felt by point charge Q placed at point B. So again, I'm going to use the formula from chapter 20, section 4, where the electric force is equal to the point charge times the electric field at the point charge location. Okay. So my force on capital Q is equal to the point charge, which is capital Q, and the electric field at that point is the E total we solved for in step 3. So it's multiplied by rho r over 4 epsilon naught. So our final answer, the force felt by point charge Q placed at point B, is going to be equal to Q rho r over 4 epsilon naught. All right, and that's the final answer for part B.